Have you ever found yourself just completely swamped by information, trying to make sense of some really complex situation with way too many
Yeah,
unknowns?
happens all the time, right?
Yeah, or maybe wished for a shortcut to really get what's happening at the cutting edge of AI, especially when it tackles those kinds of messy problems.
Well, that's pretty much what we're diving into today.
Exactly. We're taking a deep dive into how artificial intelligence navigates these worlds that are, you know, unpredictable, maybe only partially known, or even continuous. This isn't just about finding a simple path from A to B anymore.
No, it's way beyond that. It's about tackling true complexity. And our mission, for you listening, is to pull out the key insights from these advanced AI search techniques.
Okay.
We'll analyze the core ideas, maybe challenge some assumptions you might have, and hopefully reveal some surprising patterns and connections, how AI solves problems that are really far from straightforward.
Sounds good. So get ready for some thought-provoking stuff about intelligence itself. Okay, so let's unpack this different way of thinking about AI search. Usually when we hear search, we think about finding a route, right? Like getting from Arad to Bucharest on a map. You care about the steps, the journey.
Right, the sequence matters.
But what if that journey, the path itself, just doesn't matter at all? What if you only care about the final state, the destination? Think about the classic 8 queens problem on a chessboard.
Yeah. Place 8 queens so none can attack each other.
Exactly. You just need that final setup, how you got there. Totally irrelevant, right?
Precisely. And that's where local search algorithms come into play. Their whole approach is fundamentally different.
How so?
Well, they start at some state and they only think about moving to neighboring states. They don't keep track of the path they took or even where they've been before.
Really? No memory of the path?
Nope. And that's simplicity. That's actually their superpower. It means they use very little memory, tiny amounts.
Okay, that makes sense. Less overhead.
And because of that, they can find pretty reasonable solutions, sometimes even optimal ones, in these massive, astronomically huge state spaces. Even infinite ones, where those traditional pathfinding methods would just completely grind to a halt.
Wow. So they're built for a different kind of problem.
Exactly. They're designed for optimization problems. The goal isn't just any solution, but the best possible state according to some specific measure. We call that measure the objective function.
Right. So to visualize this, you mentioned this idea of a state-space landscape. Can you paint that picture for us?
Sure. Imagine the whole problem space, all possible configurations as a kind of terrain, like a mountain range. Every possible state, every solution configuration has an elevation
And that elevation is based
on how good it is according to that objective function. So if you're trying to maximize something like profit or maybe efficiency, you're looking for the highest peak in the landscape, the global maximum.
or the deepest valley if you're minimizing costs, say, the global minimum.
Exactly. It gives you this great mental model for what the algorithm is trying to do.
Okay, so how do we actually navigate this landscape? What's the most basic approach?
That would be hill climbing search. It's incredibly simple, almost intuitively obvious.
Yep.
You start somewhere, anywhere really. You look at all your immediate neighbors, the states you can reach in one step, and you always move to the neighbor with the highest value, the one that takes you most directly uphill.
So you're just following the path of steepest descent.
That's it. And you keep doing that until you reach a point where you just can't go any higher. All your neighbors are downhill or at the same level.
I like the analogy of trying to find the top of Mount Everest, but you're in a really thick fog and you've got amnesia.
Yeah, that's a good one.
You only know what's right around your feet. So you always take the step that seems to go most steeply uphill, and you stop when every step around you would actually take you down.
That captures it perfectly. And it's often called greedy local search. Greedy because it just grabs the best immediate option without looking ahead at the consequences.
Right. Greedy sounds kind of bad, but you said it can be effective.
Oh yeah, very effective sometimes, especially at making rapid progress initially. Like in that 8 queens problem, starting with a random board, hill climbing might go from, say, 17 attacking pairs down to just 1 or 2 in only a handful of steps.
Wow. So it gets you close, fast.
Very fast.
Yeah.
Almost a solution very quickly.
There's always a but, isn't there? That Mount Everest analogy makes me think, what if you climb a peak, but it's just like a foothill?
Yeah.
Not the actual summit.
Exactly. That's the big problem. The Achilles heel of simple hill climbing. Despite its speed, it has some major limitations. The first one is exactly what you said, local maxima. These are peaks, sure. They're higher than all their immediate neighbors, but crucially, they might be much lower than the true highest point, the global maximum that you're actually searching for.
And the algorithm gets stuck there.
It gets completely trapped. It thinks it's found the best spot because everywhere it looks nearby is downhill. The 8 queens example shows this perfectly. You might find a state with just one attacking pair, which is a local minimum for number of attacks, but it's not the goal state of 0 attacks.
Okay, local maxima. What else?
Then you have things called ridges. Think of a long, narrow crest. It might slope gently upwards along its length, but any step off the ridge goes steeply downhill. A greedy algorithm finds it really hard to follow that kind of feature.
Right, because the immediate sideways steps look bad.
Exactly. And finally, you can hit plateaus. These are flat areas in the landscape where all the neighboring states have the same value.
So you don't know which way to go.
Right. You might be on a flat local maximum where you're truly stuck on a flat summit, or you could just be on a shoulder, a flat area on the side of a bigger hill where progress is actually possible if you just keep moving horizontally for a bit. Hill climbing doesn't know the difference.
Okay, so these sound like pretty serious roadblocks. How do AI algorithms actually get around these? What are the tricks?
Well, it turns out sometimes the simplest tweaks can have surprisingly huge effects. One really basic idea is allowing sideways moves.
Sideways moves, you mean moving to a state even if it's not better, just the same?
Exactly. If a neighbor has the same objective function value, the algorithm is allowed to move there. The hope is that you're on one of those shoulders, not a flat peak, and that moving sideways might eventually lead you to an upward slope again.
Does that actually work?
The effect on the 8 queens problem is pretty remarkable. Standard hill climbing, maybe a 14% success rate from random starts, allow up to, say, 100 sideways moves. That success rate jumps to something like 94%.
Wow, just from allowing flat moves. That's
Yeah.
surprising.
It is. Now, it often takes more steps overall, so there's a trade-off, but getting the right answer 94% of the time versus 14%, often worth it.
Absolutely. Okay, what else?
An even more powerful strategy, especially when you combine it with the basic hill climbing, is random restart hill climbing.
Okay, sounds like what it is.
It is. It's basically the old saying, if at first you don't succeed, try again. You just run the standard hill climbing search multiple times. But each time, you start from a completely random initial state.
Ah, okay. So you're hoping one of those random starts lands you in a part of the landscape that leads to the global maximum.
Precisely. And the neat thing is, this approach makes the algorithm complete with probability 1, which means if you run it enough times, you're virtually guaranteed to find the global optimum eventually.
Even for really hard problems.
For 8 queens, it's incredibly effective. People have used it to solve n queens for n in the millions. It just highlights this amazing power you get from combining a simple, fast, greedy search with pure randomness and repetition.
That's really cool. Okay, so we've got basic hill climbing, sideways moves, random restarts. What about getting sort of fancier? Embracing randomness in a more structured way.
Yeah, exactly. And one really elegant approach here is called simulated annealing.
Annealing, like with metals.
Yeah. Exactly like with metals. It's directly inspired by the process in metallurgy where you heat metal up really hot and then cool it down very slowly.
Right, that lets the atoms arrange themselves into a low-energy, stable crystal structure.
Precisely. Simulated annealing uses that as a metaphor for finding the lowest energy state, or the global minimum maximum in our landscape.
Okay, how does the algorithm mimic that?
It basically combines hill climbing with a kind of random walk. Like hill climbing, it always accepts moves that improve the situation, moves that go uphill, in
Right.
maximizing. But here's the key difference. It also probabilistically accepts bad moves, moves that go downhill.
Whoa, okay. It willingly makes things worse sometimes. Why?
To escape those local maxima, the probability of accepting a bad move depends on 2 things: how bad the move is, how much downhill it goes, and a temperature parameter, T.
Ah, the temperature, like in metallurgy.
Right. Early on, the temperature T is high. This means bad moves are more likely to be accepted. The algorithm jumps around quite a lot, exploring widely, easily bouncing out of those local optima.
So it's like shaking the system vigorously at the start.
Kind of, yeah. Then, just like cooling metal, the temperature T is gradually decreased over time according to a schedule. As T goes down, the probability of accepting a bad move drops exponentially. It becomes more and more like standard hill climbing, focusing in on the best peak it's found.
And if you cool it slowly enough.
If the schedule is slow enough, it's mathematically proven to find the global optimum with a probability approaching 1. It's a really powerful idea.
Where is this actually used?
Oh, and lots of complex optimization problems. Things like very large-scale integration, VLSI,
Mhm.
circuit layout, optimizing factory schedules, complex logistics,
Mm.
anywhere you have a huge search space with lots of local optima.
Fascinating. Okay, so that's using randomness cleverly for one search path.
Yeah.
What about using multiple searches at once? You mentioned that earlier.
Right, moving beyond the single point, exploring the landscape. That leads us to local beam search.
Beam search, okay.
Instead of just tracking one single current state,
Mhm.
local beam search keeps track of K states simultaneously. Let's say K10.
Okay, so 10 points on the landscape.
Exactly. Then, in each step, it generates all the successors for all K of those states. That might be a lot of successors.
Right.
From that large pool of successors, it simply chooses the K best ones based on the objective function. Those become the new set of K current states for the next step.
Hmm. So how is that different from just running, say, K independent random restart searches in parallel and seeing which one does best?
That's the crucial distinction. In local beam search, useful information is implicitly passed between the parallel search threads because they're all competing for those K slots.
Ah, I see. If one search path finds a really promising area,
Its successors are likely to be among the best K chosen. So the search effort automatically focuses on the more promising areas. It allows the algorithm to quickly ditch unfruitful searches and move resources, move those K states to where, the grass seems greener.
so it's like a collaborative search effort, even though the states don't directly talk to each other.
Exactly. There's also a variant called stochastic beam search, which adds randomness to the selection of the best K, just to avoid all the states clustering too closely in one area.
Makes sense. Okay. From beams of states to, well, populations. This leads us to evolutionary algorithms, right? Drawing inspiration directly from biology.
Yeah, this is where AI gets really bio-inspired. The whole metaphor is natural selection, but applied to problem solving,
So you have a population of individuals.
which are candidate states or solutions. And the fittest individuals, the ones that score highest on our objective function, are more likely to reproduce and create the next generation of states.
And genetic algorithms are a big part of this.
They're a very prominent type of evolutionary algorithm, yes. Here, the individuals are often represented as strings, like chromosomes or DNA.
Okay, so how does the evolution happen? What's the cycle?
Typically, you start with a randomly generated initial population of these strings. Then you evaluate each one using a fitness function. For 8 queens, the fitness might be, say, the number of non-attacking pairs. Higher is better.
Right.
Then comes selection. Individuals are chosen to be parents, usually with a probability proportional to their fitness. Fitter individuals get more chances to reproduce.
Survival of the fittest.
Pretty much. Then you have crossover. This is like sexual reproduction. You take 2 parent strings, cut them at some random point, and swap the pieces to create 2 new offspring strings.
Combining traits from both parents.
Exactly. And finally, there's mutation. Small, random changes are introduced into the offspring strings, flipping a bit, changing a character just to maintain diversity and potentially introduce new beneficial traits. This whole cycle repeats for many generations.
And over time, the population should evolve towards better and better solutions.
That's the idea. And there's this concept called a schema, which helps explain why this works. A schema is like a pattern within the string, a substring with some fixed parts and some don't care positions. Genetic algorithms tend to work well when these schemas correspond to meaningful building blocks of a good solution. Crossover combines good building blocks.
Okay, and you mentioned something really interesting here earlier, a surprising pattern connection. The Baldwin effect. What's that about?
Ah, yes, the Baldwin effect. It's this fascinating observation about the interplay between learning within an organism's lifetime and evolution over generations.
Okay.
The idea is that if organisms can learn a certain advantageous trait during their life, it makes it easier for genetic evolution to eventually discover that trait too. Learning essentially smooths out the fitness landscape, making it easier for evolution to find the peaks.
So learning can actually guide or accelerate evolution.
In a sense, yes. Traits that are difficult for individuals to learn might eventually become genetically encoded, hardwired, but things that are really easy for individuals to learn during their lifetime might not need to be encoded in the genes. Evolution doesn't waste effort encoding something easily learned.
Wow. That's a deep connection between learning and evolution.
It really is. And it highlights something crucial for practical AI using genetic algorithms. Success often hinges on careful engineering of the representation. How you encode the solutions as strings really matters so that crossover and mutation can actually create meaningful improvements.
Right, the building blocks need to make sense. Okay, we've covered a lot on navigating these discrete, potentially tricky landscapes, but what about the real world? It's often not discrete squares on a board. What about continuous spaces?
Exactly. Think about trying to place, say, 3 new airports anywhere in Romania to minimize the total distance people have to travel. The possible locations aren't just grid points, they're anywhere in a continuous 2D space.
So a state isn't just one configuration. It's defined by what? N-dimensional vectors, like by 1, y1, by 2, y2, by 3, y3, for 3 airports.
Precisely. And the immediate challenge is that from any given state, there are infinitely many neighboring states you could move to just by nudging one coordinate slightly, an infinite branching factor.
Yeah, how on earth do you search that? Traditional search seems impossible.
It is, in its pure form. So we need different approaches. One simple way is discretization. You just overlay a grid onto the continuous space and pretend it's discrete. Works okay sometimes, but you lose precision.
Right, you might miss the true optimum between grid lines.
Another way is using empirical gradient methods. You sort of measure the objective function at the current point and a point nearby and estimate the slope, the gradient from that difference. It's like hill climbing, but estimating the slope numerically.
Okay, like feeling around for the uphill direction.
Kind of. But if your objective function can be expressed mathematically, you can often use calculus. You can compute the gradient directly. The gradient is a vector that points in the exact direction of the steepest uphill slope.
Ah, okay, so calculus gives you the precise uphill direction.
Exactly. Then you can do steepest descent hill climbing in continuous space. You just update your current state, the vector of coordinates, by taking a small step in the direction of the gradient. The size of that step is the step size.
Makes sense, like knowing exactly which way is steepest uphill. No fog involved this time.
Right. And there are even more advanced calculus-based methods, like the Newton-Raphson method, that use second derivatives, the Hessian matrix, to try and jump more directly towards a maximum or minimum. They can be faster, but computationally heavier, especially in high dimensions.
But you mentioned a special class of these problems that are much easier.
Yes, convex optimization. This is a really important subclass. Imagine the landscape isn't rugged with lots of peaks and valleys, but is just a single smooth bowl shape for minimization, or a single hill for maximization. That's a convex set.
So no local optima to get stuck in, other than the global one.
Exactly. Any local optimum is the global optimum. This means algorithms, often based on linear algebra, can find the perfect solution very efficiently, sometimes in polynomial time. Linear programming is a famous example of a convex optimization problem. They're extremely useful in practice when problems fit this structure.
Okay, so that handles continuous spaces. What about another real-world messiness?
Yeah.
Unpredictability. What if your actions don't always do what you expect them to?
Ah, yes. Non-deterministic actions. This happens all the time. Maybe you try to move forward, but the wheels slip and you stay put, or you try to pick something up and you drop it.
The agent doesn't know for sure which state it will end up in after acting.
Exactly. This uncertainty forces us to introduce a really core concept, the belief state.
Belief state.
It's the set of all possible physical states the agent thinks it might be in, given its history of actions and observations. If an action could lead to state A or state B, the agent's belief state after the action is the set A-B.
Okay, so it tracks possibilities. And the solution can't be just a simple sequence of actions anymore.
Nope, because the outcome of an action isn't fixed. The solution has to be a conditional plan or a contingency plan. It has to specify what action to take based on what the agent actually observes happening.
Can you give an example?
Let's go back to that vacuum world. Imagine an erratic vacuum cleaner. Maybe the suck action usually cleans the current square, but sometimes it also cleans an adjacent square. Or worse, maybe sometimes it accidentally deposits new dirt.
Oh dear, okay.
So if you're in state 1, dirty on the left, and you suck, you might end up in state 5, clean on the left, or maybe state 7, clean on the left and right square is also clean. You don't know which beforehand.
Right.
So your plan can't just be suck, right, suck. It might need to be something like suck, then if I observe him in state 5, then execute. Right, suck. Otherwise, if I'm in state 7, do nothing.
It branches based on the outcome. That sounds like it could get complicated fast.
It does. This leads to needing things like and/or search trees. The or nodes are the agent's choices, like left, right, suck. but the ANDI nodes represent the environment's unpredictable outcomes for a chosen action.
Why and nodes?
Because the plan has to work regardless of which outcome happens. It has to have a valid continuation for every branch coming out of that ANDI node. The solution itself becomes a subtree of this ANDI OR graph.
Got it. Handle all possibilities.
And sometimes dealing with non-determinism leads to cyclic solutions. Imagine that slippery vacuum world again, where the right action sometimes just fails, leaving you in the same state.
Oh.
A valid plan might be, suck, then while I'm still in state 5, keep trying.
Right.
Then suck again once I reach state 7. You just keep trying the action until it works.
So loops become part of the plan.
Exactly. But whether a cyclic plan works depends on the nature of the non-determinism. If it's random chance, like eventually right will succeed, a loop is fine. If it's based on some hidden fact you don't know, a loop might just run forever.
Tricky distinctions.
Huh?
Okay, so we have continuous spaces, unpredictable actions. What about not even knowing where you are or what's around you? Partially observable environments.
Right. This is maybe the most challenging scenario, often called operating in a fog of war. You don't have complete information about the state of the world.
What's the most extreme version of this?
That would be sensorless problems, sometimes called conformant problems. The agent gets literally no sensory input, no percepts at all.
No sensors. How can it possibly solve anything? It sounds impossible.
It does, but surprisingly, solutions can exist. The key is that belief state again. If the agent has no idea where it starts, its initial belief state might just be the set of all possible states in the environment.
Okay, so it starts thinking it could be anywhere. How does acting help if it gets no feedback?
Because actions transform the belief state. Imagine you're in one of 2 possible rooms, room A, room, but you don't know which. If you perform the action go through door, and you know that in room A, the door leads to room C, and in room the door leads to room D, then after the action, your new belief state is room C, room D. You still don't know exactly where you are, but you know more than before.
Ah, I see. The search isn't in the physical state space, it's in the space of belief states.
Exactly. And the belief state space is fully observable. The agent always knows its own current belief state, the set of possibilities. So you can search for a sequence of actions that drives any initial physical state into a goal state.
Can you really guarantee reaching a goal without knowing where you started?
Sometimes, yes. This is called coercion. For example, in a simple 2-square vacuum world, the action sequence right suck, left suck might guarantee that you end up in the goal state clean on the right, no matter which of the 8 possible start states, location, dirt status you began in. You coerce the world into the state you want.
That's amazing. But tracking sets of states sounds computationally expensive.
Oh, it definitely is. The number of possible belief states can be exponential in the number of physical states, 2n. So for large problems, this is often intractable. People use techniques like pruning redundant belief states or clever incremental belief state search methods to try and manage this complexity.
Okay, so that's the extreme no sensors case. What if you do get some information, just not complete information, like sensors that only tell you about your immediate vicinity?
Right, that's the more common scenario of partial observability. You have a percept function. It tells you what sensor reading you'd get in any given state. For instance, in the vacuum world, maybe you can only sense if your current location is dirty or clean and whether there's a wall immediately in front.
So if you're in state 1 left square dirty, maybe you perceive L dirty. But maybe state 3 left square dirty, but right square is also dirty, gives the same percept.
Exactly. Your percept doesn't uniquely identify the state. So when you get a percept, your belief state updates. If you thought you might be in state 1, state 2, state 3, state 4, and you perceive L dirty, you know you must be in either state 1 or state 3. Your belief state shrinks to state 1, state 3.
So observations reduce uncertainty. How does this combine with actions?
The belief state transition becomes a 3-stage process. First, after you take an action, you predict the resulting belief state based on how the action affects all the states currently in your belief set.
Okay, that gives you a new set of possible states.
Second, you figure out what possible percepts you might receive in that predicted belief state.
Right, because different states in the set might give different sensor readings.
And third, for each possible percept you might receive, you update your belief state again, keeping only those predicted states that are actually consistent with the percept you got. Observations can only help reduce uncertainty. They prune possibilities.
This sounds like what happens in robotics, maybe. Like a robot trying to figure out where it is in a building.
Absolutely. This process is fundamental to localization. Imagine a robot moving down a corridor using sonar sensors. Its movement might be slightly unpredictable, nondeterministic, and its sensors might be noisy. It starts with a broad belief state. It could be anywhere along the corridor. But as it moves and gets sensor readings, like wall detected 5 meters ahead, its belief state continuously updates and usually shrinks rapidly. Often it can converge to a single point. The robot becomes highly certain of its exact location, even with unreliable motion and sensing.
That's really powerful, combining action and perception to reduce uncertainty over time. Okay, this leads us naturally to the final piece. What if the agent doesn't even know the rules of the world beforehand? It has to learn as it goes.
Exactly. This is online search. It contrasts with everything we've mostly discussed so far, which falls under offline search.
What's the difference?
Offline search assumes you know the environment, the map, the action outcomes, etc. You compute a complete solution, a full plan, before you take the first step in the real world. Online search is different. The agent interleaves computation, sensing, and acting. It explores the actual world, not just a model of it.
Why would you do that?
Because sometimes the world is too complex to model accurately, or it's dynamic and changes over time. Or maybe you just have no prior map at all. The agent has to use its actions as experiments to figure things out.
But isn't that dangerous? What about dead ends? Falling off cliffs?
That's the big challenge. Online search often assumes the environment is safely explorable. This means that a goal state is reachable from any other reachable state. Often this implies actions are reversible, like in a maze where you can always backtrack. You can't afford catastrophic, irreversible actions if you're exploring online without a map.
Okay, so in a safe environment, how does an online agent work? What's a basic approach?
A simple one is the online DFS agent, based on depth-first search. It explores the physical environment. When it enters a new state, it marks it and tries an unexplored action. If it hits a dead end, all actions lead to visited states. It physically backtracks. It builds up a map of the explored portion of the state space as it goes.
How well does that work?
It's guaranteed to explore the entire reachable part of the environment eventually, visiting every link twice, once going forward, once backtracking. So it's efficient for exploration, but for finding a specific goal, its path could be terrible. It might wander off on a huge, long excursion down one path before finally backtracking and finding a goal that was nearby all along. Its competitive ratio compared to an optimal path can be arbitrarily bad.
And you mentioned it's not very bright.
Right. It learns the specific outcome of an action from a specific state, up from all at one leads to twan, but it doesn't generalize. It doesn't learn the rule like up generally increases the y coordinate unless there's a wall. It just builds a lookup table map.
Okay, so we need something smarter, something that learns more effectively as it explores.
Exactly. And a really neat algorithm for this is learning real-time A, or LRTA.
LRTA, okay, how does that work?
Think of it as hill climbing, but with memory. It keeps track of the states it has visited and maintains a current best estimate of the cost to reach the goal from each visited state's ES. Initially, these estimates might just be based on a simple heuristic like straight line distance.
So it had an estimated cost to go, like a search.
Yes, but here's the learning part. Every time the agent moves from state ES to state's prime, it observes the actual cost of that step, say CS, A, SS. It then updates its estimated cost for the state it just left,
Yeah.
HSS it updates, to be the cost of the step it just took, plus the estimated cost from where it landed, HS.
So it propagates cost information backward as it moves, learning from experience.
Precisely. It refines its cost estimates based on real-world exploration. And when deciding where to move next, it chooses the neighbor's prime that minimizes CSAS plus H's. It's trying to move towards the neighbor that looks cheapest to get to the goal from, based on current estimates.
And you mentioned it has this interesting principle, optimism under uncertainty.
Yes. This is a core design idea in LRTA and similar algorithms. When it encounters a state it hasn't visited before, or considers an action it hasn't tried from the current state, it acts optimistically. It assumes the cost from that unknown state to the goal is the best possible, perhaps zero or just the basic heuristic estimate.
Why be optimistic?
It encourages exploration. By assuming unknown territory is cheap and promising, the agent is motivated to go check it out rather than just sticking to familiar paths that might be suboptimal. It actively seeks out the unknown.
That's a great principle. Does LRTA work well?
Yes, it's guaranteed to eventually find a goal in any finite, safely explorable environment. And while its worst-case performance for exploring in states can be 0 and 2 steps, in practice, it's often much, much better. The cost estimates H's converge towards their true values over time.
And you said it connects to a broader field.
Right. LRTA is actually considered a special case of reinforcement learning algorithms. Reinforcement learning is this whole huge area of AI focused on agents learning optimal behaviors through trial and error, receiving rewards or penalties from the environment.
So this online search isn't just about finding a path, it's fundamentally about learning.
Absolutely. That's the final crucial piece of the puzzle. These online agents are learning a map of the environment, which actions lead where. They're learning more accurate cost estimates, getting better heuristics.
And what's the ultimate goal here? Where's this research heading?
The big goal, the future direction, is for agents to move beyond just learning maps or cost tables. We want them to learn general rules from their observations, like figuring out pushing an object usually makes it move forward unless it's too heavy, or turning the light switch changes whether the room is lit. This requires new kinds of representations and algorithms that can build these abstract rules from raw experience.
Thus.
That's where a lot of exciting research is happening now.
Wow, okay, what a journey we've taken. We started with simple hill climbing, just trying to walk uphill in a foggy landscape.
And ended up with agents that explore unknown worlds, learn maps, update their beliefs about reality based on sensor readings, and even learn general rules on the fly.
Yeah, it really shows the progression of how AI tackles environments that are anything but simple and predictable. And we saw how inspiration comes from all over the physics of annealing metals, the processes of biological evolution.
And even just the basic logic of how we navigate with partial knowledge, using belief states. What's really fascinating, I think, is seeing how these concepts are so deeply interconnected.
How so?
Well, you start with memory-efficient local search. Then you add randomness and population dynamics inspired by nature to escape local traps. Then you explicitly tackle uncertainty using belief states for nondeterminism and partial observability. And finally, you combine it all with online learning to adapt in totally unknown settings. It's a progression from assuming a fixed path to embracing adaptive exploration.
That interconnectivity really highlights the richness of the field. These aren't just isolated tricks, they build on each other.
Exactly. And looking at these connections, seeing how AI tries to solve these fundamental problems of navigating complex, uncertain worlds, it definitely suggests novel research directions for making AI even more capable and adaptable.
And, as we wrap up this deep dive, it makes you think how incredibly similar these AI challenges are to our own lives, right?
Absolutely.
You're constantly operating in partially observable, non-deterministic, often unknown environments. We're always trying to find a good state, happiness, success, understanding, learning, and adapting as we go.
We're all online search agents, in a way.
Totally. So here's a thought to leave you with. What if we, like that LRTA agent, could more explicitly track our own cost estimates towards our goals? What if we consciously embrace that optimism under uncertainty when facing the unknown in our own complex decision-making?
Interesting question.
What novel insights might that suggest for our own research directions in life as we navigate these incredibly complex landscapes we find ourselves in?
Something to definitely ponder. Keep exploring, keep questioning those connections, and keep taking those deep dives.